Welcome, everyone, to a very special Halloween episode of Saltwater Stories.
Ooh, indeed. And we promise things might get just a little bit scary today.
They really might. We're setting the stage for a truly incredible ocean story, but fair warning, it involves
Hmm.
some spooky happenings beneath the waves.
Sounds intriguing. Are we talking sea monsters? Ghost ships?
Ha! Not quite sea monsters in the traditional sense, but maybe something even more mysterious. We're actually going on a mission today. Think of us as ocean detectives.
Ocean detectives. I like it. What case are we cracking?
We're investigating these strange, silent spots in the ocean, places where it seems like the ocean just forgets how to breathe.
Forgets how to breathe. Wow, okay, that does sound a bit chilling. You mean areas where there's no air or oxygen?
Exactly. Vast stretches of water, sometimes covering hundreds of square miles, where the oxygen levels drop so low that most marine life, they just can't survive there.
So like underwater deserts, but caused by a lack of air.
Precisely. Imagine bustling underwater neighborhoods suddenly turning into these silent, empty zones. It's a real environmental puzzle.
Okay, you've definitely got my attention. This sounds like a major mystery. What are these spooky zones officially called?
They have a name that fits our Halloween theme perfectly. We're investigating the chilling phenomenon known as ocean dead zones.
Ocean dead zones. Wow. Okay, that paints a picture.
It really does. And to understand what it's like, maybe we can start with a quick story. Imagine you're a little fish, maybe Finley the red drum, or perhaps Clara the blue crab.
Okay, I'm picturing Clara the crab scuttling around her neighborhood. Lots of other critters around.
Yeah, normally it's a busy place full of life, food, hiding spots. But then one day the water starts to feel different. Kind of thick, heavy maybe.
Heavy water. How so?
It's hard to explain from a human perspective, but for Clara, it's like the very essence of the water is changing. Maybe her older, wiser cousin suddenly scuttles over, shouting, "We have to go, now!"
Oh, wow. An emergency. Why? What's happening?
They don't know exactly, but they feel it. It's getting harder to breathe. They have to escape, swim, or crawl away as fast as they can.
But what about their friends? The slower ones?
That's the scary part. As Clara scrambles away, she looks back and sees her friends, the sea stars, the clams, the little worms. They can't move fast enough. They get left behind.
Left behind in the heavy water.
Yes, left behind in this silent, murky water that's run out of the gas. They all need to breathe. The whole neighborhood becomes an underwater desert, a biological desert.
Because there's no oxygen.
Exactly, no dissolved oxygen. That invisible gas mixed into the water that fish and crabs and oysters need to live.
So an ocean dead zone is basically an area where the oxygen levels are just too low for most animals.
That's the core of it. So low that most animals either have to flee like Clara or they suffocate. The scientific name for this low oxygen condition is hypoxia.
Low oxygen.
Right. And our mission today as ocean detectives is to figure out the secret step-by-step recipe that creates these terrifying dead zones.
A recipe for disaster, sounds like.
It can be. But the good news is we'll also investigate how we can become ocean heroes and help these zones breathe again. There's hope in this story, too.
Okay, I'm ready. Let's dive into the spooky science. Where do we start? How does oxygen even get into the water in the first place?
Good question. You mentioned dissolved oxygen. It's invisible, right? Like if you dissolve sugar in water, you can't see the sugar anymore, but it's there.
Exactly. Oxygen gas from the air dissolves into the water, mostly right at the surface. Think about waves crashing, winds stirring things up. That helps mix the air in.
Ah, okay. So the surface gets oxygen from the air. What else?
The other big source is underwater plants. Tiny microscopic plants called phytoplankton. They do photosynthesis, just like plants on land.
And photosynthesis makes oxygen, right? I remember that from school.
You got it. So these tiny plants produce oxygen near the surface too. And fish and other animals use their gills to pull that dissolved oxygen out of the water to breathe.
So gills work like our lungs, but for water.
Okay.
Right. But what happens in a dead zone? Does the oxygen just disappear?
In a way, yes. The level drops dangerously low. Think of it like imagine a big, crowded room, maybe a Halloween party.
Okay, noisy party, lots of people.
Right. But now imagine someone seals all the windows and doors shut, completely airtight.
Uh-oh, that sounds bad. People are breathing.
Exactly. Everyone keeps breathing, using up the oxygen in the room, but no fresh air can get in because everything's sealed.
So the air would run out. People would be in trouble.
Precisely. A dead zone is like that sealed room. The processes that normally supply oxygen get cut off, or more often, something starts using up the oxygen much faster than it can be replaced. Anything that can't leave that room, that area of low oxygen, is in real danger.
Wow, that's a scary analogy. So the term dead zone is Completely empty. No life at all.
That's a common misconception. The name is dramatic, and for the animals, we usually think of fish, crabs, shrimp, oysters that might as well be dead. They disappear. But it's not totally empty. It's often full of tiny life forms, like certain kinds of bacteria and microbes. These are specialists that can actually survive or even thrive without much oxygen.
So the type of life changes completely, from a busy neighborhood to something else.
Exactly. It shifts from a complex ecosystem we recognize to one dominated by these microbes. It's a biological desert for the bigger creatures.
Okay. And you mentioned these zones aren't all the same, like ghosts. Maybe some appear and disappear.
That's a great way to put it. They're not all identical. The most common type we worry about are seasonal dead zones.
Seasonal. Like they only show up in summer.
Mostly, yes.
Yeah.
They typically form in the spring and summer when the water gets warm and certain conditions align, which we'll get into. Then in the fall or winter, storms or colder weather might mix the water up again, and the dead zone breaks apart or shrinks.
So they come and go with the seasons. Are there other kinds?
Yep. Sometimes you get temporary dead zones. These might pop up just for a few hours or a couple of days, maybe after a really heavy rainstorm washes a lot of stuff into the water. Very fleeting.
Huh. And terminal ones. Do they exist?
They do. There are some areas, usually in very deep parts of the ocean or in specific basins like the Black Sea, where low oxygen is actually the natural state of things because the water just doesn't circulate much down there. We call those permanent dead zones.
Okay, so some low oxygen zones are natural, but the problem is the new ones.
Exactly. The big worry, the global environmental crisis, is about the hundreds of new dead zones that have appeared in coastal areas, mostly caused by human activities. And there's even a really weird type called diel cycling hypoxia.
Dial cycling. What on earth is that?
It's bizarre. Diel means over a 24-hour period. In these places, the oxygen disappears at night but then comes back during the day.
At night, how does that work?
It often happens in shallow areas with lots of algae. During the day, the algae are photosynthesizing like crazy, pumping out oxygen. But at night, they stop photosynthesizing and only respire, breathe in oxygen just like animals do. If there's a ton of algae, they can actually use up most of the oxygen overnight.
Wow, that's wild. A daily cycle of near suffocation.
Yeah.
Okay, so we have seasonal, temporary, permanent, and this spooky dial cycling kind. But you mentioned hundreds of new zones caused by humans. Just how big is this problem globally?
It's huge and growing. Scientists now estimate there are over 500 of these human-caused dead zones around the world, maybe even more, as some are hard to detect.
500. That sounds like a lot. Can you give us a sense of the scale? Like how much area are we talking about?
Well, if you could somehow take all those dead zones and stitch them together into one giant patch,
Yeah.
that patch would cover an area larger than the entire United Kingdom.
Whoa, larger than the UK. That's enormous and scary.
It is, and what's even scarier is how quickly this has happened. We need to look at the timeline.
Okay. When did these things start appearing?
Back in the 1950s, maybe early 60s, scientists knew of fewer than 50 coastal areas with hypoxia problems worldwide. Fewer than 50.
And now it's over 500.
At least. The number has just
So scientists say it's grown explosively in the last 60, 70 years.
explosively. So this isn't some ancient mystery. This is something relatively new, and it's tied to us.
Overwhelmingly, yes. The timing lines up perfectly with big changes in human activity, especially things like modern farming and growing populations along coastlines.
Okay, so that brings us to the recipe of doom you mentioned. How do humans accidentally create a dead zone? What's the process?
The scientific name for this whole process is eutrophication. It sounds complicated, but it basically means the water gets overloaded with nutrients. Too much of a good thing.
Eutrophication. Okay, another big word. Can we break down the recipe step by step?
Absolutely. Think of it as a 5-step recipe. And step 1 is what we call the nutrient flood.
A flood of nutrients. Specifically, two main ones, nitrogen and phosphorus. These are like super powerful vitamins for plants. Plants need them to grow.
Okay, nutrients are good, plants need them. What's the problem?
The problem is getting way, way too much of them all at once. It's like instead of a balanced meal, you suddenly dump truckloads of pure vitamins into the water. An overdose.
An overdose of nutrients. Where does this flood come from?
We'll get into the specific sources later, but think farms, cities, wastewater, lots of places. This nutrient flood acts like throwing a giant all-you-can-eat buffet for the tiny microscopic plants floating in the water.
The phytoplankton, the algae we talked about.
Exactly, which leads directly to step 2, the green monster party, or what scientists call an algal bloom.
Green monster party. I like that. So the algae just go crazy eating all those nutrients.
They multiply at an incredible speed, uncontrolled growth. The water can turn thick and soupy, often green, sometimes brown or even red. It becomes this massive bloom of algae.
Okay, a giant algae party. That sounds messy. Does it cause problems itself?
Oh, definitely. First, this thick layer of algae at the surface acts like a giant sunshade.
A sunshade,
Oh.
blocking the light.
Yep. It blocks sunlight from reaching plants that live on the seafloor, like seagrasses. Those plants need light too, and when they don't get it, they wither and die.
Oh, so it hurts the plants living deeper down. What else?
Well, the party can't last forever. Eventually, the algae run out of nutrients or just get too crowded, and they start to die off. Huge amounts of them.
So the green monster party ends.
Yeah.
And then what?
Then comes step 3, the oxygen heist. All those dead algae sink down to the bottom.
Down to the seafloor, like a big layer of gunk.
Exactly. A thick sludge of dead, decaying algae covers the bottom, and this attracts the ocean's cleanup crew.
Cleanup crew. You mean bacteria?
Precisely. An army of bacteria swarms in to decompose all that dead algae. They start breaking it down, essentially eating it.
Okay, bacteria cleaning up the mess. That sounds good.
It would be, except for one crucial, spooky detail. As these bacteria eat or decompose the algae, they breathe.
They breathe.
Yeah.
Like we do, using oxygen.
Yes. They perform aerobic respiration, which uses up dissolved oxygen from the water around them. And because there is so much dead algae to decompose after a massive bloom,
Oh no, don't tell me.
the bacteria use up oxygen incredibly fast. Much, much faster than it can be mixed down from the surface. They literally gulp all the available oxygen out of the bottom water. That's the heist.
Wow. So the cleanup crew accidentally steals all the oxygen needed by the fish and crabs down there. That's sinky.
It's a natural process gone wild because of the sheer amount of dead stuff we fed it with the nutrient flood.
Okay, so the bottom water loses its oxygen. But why doesn't fresh oxygen from the surface just mix back down? You said waves and wind mix it in.
Ah, that brings us to the trap. Step 4, the layer cake trap, or what scientists call stratification.
Layer cake. Like
Wow.
the water forms layers.
Exactly, especially in the summer and especially where rivers meet the sea. You get warm, lighter, fresh water flowing out from the river on top.
Okay, warm river water on top.
And underneath, you have the colder, saltier, denser ocean water. Warm, fresh floats on cold, salty. They don't easily mix.
Like oil and water, kind of stay separated.
Very much like that. This layering effect is called stratification. It creates a really strong boundary, almost like a lid, between the surface water and the deep water. Scientists call this boundary the pycnocline.
Pycnocline. Okay, another big word. So this lid, it traps the water underneath.
It does. It acts like a physical barrier, preventing the oxygen-rich surface water from mixing down into the deeper water where the bacteria have used up all the oxygen.
So the oxygen heist happens below, and the lid keeps fresh air from getting in. The dead zone is locked in place.
Precisely. At least until something powerful enough, like a strong autumn storm or winter cooling, comes along to break up that stratification and mix the water column again.
Wow, that's a deadly combination.
Yeah.
Nutrient flood, algae party, oxygen heist, and the layer cake trap. That's the recipe.
That's the core recipe for eutrophication leading to hypoxia. But there's one more factor that's making everything worse.
Oh no, what's that?
Climate change. Our warming planet acts like a threat multiplier here.
How does a warmer planet make dead zones worse?
2 main ways. First, simple physics. Warmer water just can't hold as much dissolved gas as cold water. Think of a warm soda going slap faster than a cold one.
Ah, right. Less fizz, less oxygen.
Okay.
So as the ocean warms, it naturally holds less oxygen to begin with. Second, warmer surface water makes that stratification, that lid, even stronger and lasts longer into the year.
So the temperature difference between the warm top and the cold bottom gets bigger, making the lid harder to break.
Exactly. It strengthens the barrier, making it harder for oxygen to mix down and allowing the low oxygen conditions to persist for longer periods. Climate change basically pours gasoline on the eutrophication fire.
Okay, this is making scary sense now. We've got the recipe. Now we need to find the suspects. Where is this flood of nutrients, the nitrogen and phosphorus, actually coming from? We need to trace the clues.
Right, detective. Let's follow the nutrient trail back to its sources. There are 3 main culprits we need to investigate.
Suspect number 1. The single biggest source, often responsible for something like 70 to 80% of the nutrient pollution in many places, is agricultural runoff from farm fields.
Farms. How? Fertilizer.
Exactly. Modern farming often uses a lot of fertilizer, rich in nitrogen and phosphorus, to help crops grow big and fast. But the crops don't always use it all up.
So the extra just sits there.
And then when it rains, that excess fertilizer, along with animal manure from livestock operations, gets washed off the fields.
Washed away into streams and rivers.
Yep. It runs off the land and into ditches, streams, and eventually rivers that flow towards the coast. Some crops, like corn, are also known for being a bit leaky. They don't hold on to nitrogen very well, so more escapes into the environment.
Okay, so farms are a major source. Suspect number 2.
Our towns and cities, urban and suburban areas, contribute quite a bit too.
How don't have huge fields of crops in the city?
No, but think about lawns. People use fertilizer on their grass, right? That can wash off sidewalks and driveways when it rains.
Lawn fertilizer.
Yeah.
What else?
Pet waste. When people don't scoop the poop, that waste, which is full of nitrogen, gets washed into storm drains.
Ew, really? Dog poop causes dead zones.
It contributes. Every little bit adds up. And then there's wastewater, the water that goes down our sinks, toilets, and showers.
But doesn't that get treated at a sewage plant?
It does, but wastewater treatment plants aren't always designed to remove all the nitrogen and phosphorus. Some nutrients still get released in the treated water. Plus, heavy rain can sometimes overwhelm systems, causing overflows of untreated sewage.
Yikes. Okay, so farm runoff, city runoff, including lawns and pet waste, and wastewater. Is that all?
There's one more, often invisible suspect: the air around us.
The air. How does air pollution cause water pollution?
When we burn fossil fuels in cars, trucks, factories, power plants, it releases nitrogen compounds into the air. Nitrogen oxides, or narcox.
Okay.
This nitrogen pollution can travel hundreds of miles through the atmosphere. Then it falls back to Earth, often with rain or snow. This is called atmospheric deposition.
So pollution from car exhaust in one place can literally fall out of the sky and land in a river or lake somewhere else.
Precisely. It adds nitrogen directly to the watershed, contributing to that nutrient flood heading towards the coast.
Wow, the connections are huge. Which brings us to that example you mentioned earlier, the Mississippi River. How does that work as a giant funnel?
It's the perfect, unfortunately devastating example. The Mississippi River Basin is enormous. It drains water from 31 different U.S. states.
31 states. That's almost 2/3 of the country, isn't it?
It covers 41% of the continental U.S., yeah. It's like a giant funnel collecting water and everything dissolved or suspended in it from all that land.
So all the farm runoff from Iowa, the city runoff from Chicago, the factory emissions from Ohio,
Yeah.
it all potentially ends up in the Mississippi.
A significant portion of it does. It gathers all those nutrients from farms, cities, and the air across that vast area and channels it all downriver.
And where does it all empty out?
Into the Gulf of Mexico, right off the coast of Louisiana and Texas.
Creating that huge seasonal dead zone we talked about.
Exactly. Actions taken on a farm hundreds of miles inland in Minnesota, or choices made about wastewater treatment in Missouri, have a direct impact on the shrimp and fish living or trying to live in the Gulf.
It really shows how interconnected everything is. And globally, this isn't just a Mississippi problem, right?
Not at all. Globally, human activities, primarily agriculture and fossil fuel burning, have basically doubled the amount of nitrogen flowing through the Earth's ecosystems compared to natural levels.
Double the nitrogen. Wow. What about phosphorus?
That's even more dramatic. We've tripled the amount of phosphorus cycling through the environment, mostly due to fertilizer use and mining.
Double nitrogen, tripled phosphorus. We've fundamentally messed with the planet's nutrient cycles.
We really have. And these ocean dead zones are one of the most visible and frankly scary consequences of that massive alteration.
Okay, let's shift perspective now. We know how dead zones form. What is it actually like for the creatures caught in them? You mentioned the underwater emergency.
It truly is an emergency for them, life or death. The entire food web gets thrown into chaos. We basically see two groups of animals with very different fates.
Two groups.
Yep. First, you have the fugitives. These are the animals that can move and move relatively quickly. Fish, shrimp, most crabs.
Claire the crab from our story earlier, the ones that get away.
Exactly. They sense the oxygen dropping and they have to flee. They swim up or swim sideways, trying to find water they can actually breathe in.
But where do they go? Are there safe places nearby?
Sometimes. But often they end up crowded into smaller areas of healthy water around the edges of the dead zone.
Crowded together. That doesn't sound good either.
It's not ideal at all. Suddenly you have way more competition for food and hiding places in that smaller area. Plus, being all bunched up makes them much easier targets for predators and for fishing boats.
Ah, so escaping the dead zone creates new problems. Stress, competition, getting caught more easily.
Definitely. It disrupts their normal lives and behavior patterns significantly.
Okay, so those are the fugitives. What's the other group?
The second group. Well, these are the trapped.
The trapped. Oh no, these are the slow ones.
Yes. Think about animals that live on the bottom and can't move much or move very slowly. Clams, oysters, mussels, sea stars, many types of worms, sponges. Scientists call them sessile or benthic organisms.
They're stuck there when the oxygen disappears.
They are. They have no way to escape the suffocating water, so tragically, they often die. Mass die-offs can occur.
Oh wow. So the seafloor becomes like an underwater graveyard.
That's a very fitting, if grim, description. The complex community of bottom dwellers can be wiped out, leaving behind only those specialized microbes we mentioned earlier, the ones that don't need much oxygen.
That's incredibly sad. Do we know how they react? Do they sense it coming?
We have some observations. For example, studies have shown crabs caught in hypoxic water displaying restless and erratic movements. They seem frantic, desperate to escape, but unable to find a way out.
That's awful to imagine. And things like oysters, they can't move at all, right?
Right. Oysters are filter feeders. When the oxygen gets low, they might clam up initially, but they can't stay closed forever. Low oxygen stresses them, makes it hard for them to filter food, and ultimately they just can't survive prolonged periods of hypoxia.
So even the animals that manage to escape, the fugitives,
Hmm.
they might not be totally okay. Right, you mentioned invisible wounds.
Yes, exactly. Even if an animal survives a brush with hypoxia or lives on the edge of a dead zone in lowish oxygen, it can suffer what scientists call sublethal effects.
Sublethal, meaning it doesn't kill them directly, but still harms them.
Precisely. The stress of living in low oxygen takes a toll. It can mess with their internal workings, their hormones.
Oh, what kind of effects?
A big one is reproduction. Low oxygen can make it much harder for fish and shellfish to reproduce successfully. They might produce fewer eggs, the eggs might not develop properly, or their spawning behavior gets disrupted.
So fewer baby fish and crabs in the future.
That's a major concern. It can impact the recovery and long-term health of the whole population. Another big sublethal effect is stunted growth.
Stunted growth. They don't get as big.
Right. It takes energy to deal with low oxygen, energy that would normally go into growing. So animals exposed to hypoxia often grow more slowly and don't reach their full potential size.
Is there evidence of that?
Oh, yes. A classic example comes from the Gulf of Mexico shrimp fishery. In years when the dead zone is really large and lasts a long time, the shrimp that fishermen catch are, on average, noticeably smaller than in years with a smaller dead zone.
Wow, so the dead zone is literally shrinking the shrimp. That must have an economic impact too.
Absolutely. Which brings us to the economic ghost haunting these dead zones. They are surprisingly expensive.
How expensive? Can we put a number on it?
It's tricky to calculate everything, but one widely cited estimate suggests the Gulf of Mexico dead zone alone costs the U.S. seafood and tourism industries about $82 million every single year.
$82 million a year. Just from the Gulf dead zone. Wow.
Well, think about the fisheries. Fishermen have to travel farther, burn more fuel, and spend more time searching for fish or shrimp that have been displaced by the dead zone. Their costs go up, and their catches might go down or be less valuable if the animals are smaller.
Okay, hitting fishermen's wallets hard. What about tourism?
Dead zones themselves aren't usually tourist attractions, but sometimes the same conditions that cause dead zones, those massive algal blooms, can be directly harmful. Some algae produce toxins.
Harmful algal blooms, or HABs, red tides.
Exactly. These HABs can cause fish kills, contaminate shellfish, making them unsafe to eat, and even cause skin rashes or breathing problems for people at the beach. That can shut down beaches, scare away tourists, and devastate coastal economies that rely on summer visitors.
So ecological disaster, animal suffering, and a huge economic cost. This is a really serious problem. Let's look at some specific locations. Where are the biggest, most notorious dead zones? Can we open some case files?
Let's do it. Case file number 1. The Gulf of Mexico Giant. We've talked about it already. It's the second largest human-caused dead zone in the world.
Fed by that massive Mississippi River funnel, right? How big does it actually get? You mentioned the size of New Jersey.
In some really bad years, yes, it has reached over 8,500 square miles, which is roughly the size of New Jersey. That's enormous. But it varies a lot year to year depending on rainfall and river flow.
So like in 2025, you said it was smaller.
Right. The official measurement for 2025 was 4,402 square miles. Still huge, bigger than Delaware and Rhode Island combined, but smaller than the record years.
And it's a seasonal mystery, right?
Yeah.
It appears and disappears.
Yep. It follows that classic seasonal pattern. It starts forming in the spring as river flow increases and the water warms up, peaks in the late summer when stratification is strongest, and then usually breaks up in the fall or winter due to storms or cooling temperatures mixing the water. Then rinse and repeat the next year.
A recurring nightmare for the Gulf ecosystem. Okay, case file number 2.
Let's head to the East Coast, the Chesapeake Bay Challenge. This is the largest estuary, a place where freshwater rivers meet the salty ocean in the United States.
The Chesapeake. I've heard it's had problems for a long time.
It has. Reports of low oxygen actually date way back to the 1930s. The bay is naturally set up for strong stratification because of all the freshwater rivers flowing into that semi-enclosed salty bay. That makes it really sensitive to nutrient pollution.
But it's naturally vulnerable, and then we added pollution.
Exactly. Nutrient runoff from farms and cities in 6 different states flows into the bay. For decades, it was really suffering, a classic example of eutrophication.
But you called it a challenge. Is there hope there?
There is, and this is really important. The Chesapeake Bay is also one of the world's biggest environmental success stories in progress.
Really? What happened?
Decades of incredibly hard work, cooperation between states, new laws limiting pollution, upgrades to wastewater treatment, farmers adopting better practices, restoring wetlands, a massive coordinated effort.
It's working. The dead zone is shrinking.
The long-term trend is positive. It still varies year to year, but on average, yes, it's getting smaller. And here's some amazing news. The 2023 dead zone was the smallest ever recorded since consistent monitoring began back in 1985.
Wow. The smallest on record. That's fantastic. It shows we can fix this.
It absolutely does. It takes time, money, and commitment, but it proves these dead zones aren't necessarily permanent scars.
Okay, that's genuinely hopeful. What's our third case file?
Let's travel to Europe, to case file number 3, the Baltic Sea's broken food web.
The Baltic Sea. I've heard that's got major problems too.
It does. It's a large, shallow, semi-enclosed sea with very limited water exchange with the Atlantic. This means pollution tends to get trapped there and build up over time. It actually contains 7 of the world's 10 largest dead zone areas. It has the biggest overall dead zone problem on the planet.
7 of the top 10. Wow. Is it just the trapped pollution?
That's a huge part of it, but the Baltic has a unique, tragic twist to its story. The dead zone crisis there was made much, much worse by humans messing up the food web, specifically by overfishing cod.
Overfishing cod. How did that make the dead zone worse? Fish don't make oxygen.
But think about what cod eat. Cod are top predators in the Baltic. They eat smaller fish, particularly a fish called sprat.
Okay, cod eats brat.
Sprat, in turn, love to eat tiny little animals called zooplankton.
Zooplankton, like microscopic critters.
Yep. And guess what zooplankton eat?
Let me guess. The algae, the phytoplankton.
Bingo. Zooplankton are the natural grazers that help keep the algae populations in check.
Right.
So you have cod eating sprat, sprat eating zooplankton, and zooplankton eating algae. A balanced system.
Okay, a food chain. What happened when the cod were overfished?
When the cod disappeared due to intense fishing, their main prey, the sprat, had no predators left, so the sprat population exploded.
Loads more sprat, eating all the zooplankton.
Exactly. This huge army of sprat wiped out the zooplankton, and with the zooplankton grazers gone.
Like the algae could just grow completely out of control, even more than the pollution alone would have caused.
Precisely. Removing the top predator caused the whole food web to crash downwards, allowing the algae to bloom uncontrollably, die, sink, and fuel, and even worse oxygen depletion than the nutrients alone would have. It's a powerful lesson.
Wow. Everything really is connected. Messing with one part, like fishing, can have these huge unexpected consequences for something seemingly unrelated, like oxygen levels.
It's a stark reminder that managing these problems requires thinking about the whole ecosystem, not just the chemistry.
These case files are eye-opening. From the giant seasonal zone in the Gulf to the hopeful recovery in the Chesapeake to the food web disaster in the Baltic. It seems pretty grim, but you mentioned success stories earlier. Can these dead zones actually recover?
Yes. And this is the crucial message of hope. They are reversible if we stop feeding them the nutrients. The absolute best proof comes from the Black Sea comeback.
The Black Sea. I thought you said parts of it were naturally low oxygen.
Deep parts are yes. But in the 1980s, the shallower northwestern shelf, fed by major European rivers like the Danube, developed a huge human-caused dead zone, about 40,000 square kilometers. It was massive, driven by intense fertilizer use in the surrounding countries.
Okay, another giant dead zone caused by pollution. What happened?
Something completely unplanned. In the early 1990s, after the collapse of the Soviet Union, the economies of many Eastern European countries went through massive changes. State-controlled agriculture and heavy industry faltered.
So like factories closed, collective farms changed.
Exactly. And one major side effect was that the use of cheap, state-subsidized chemical fertilizer plummeted almost overnight. It wasn't an environmental policy, it was an economic accident.
An unintentional experiment in cutting pollution. What was the result?
It was stunning. Within just a few years, the amount of nitrogen flowing down the rivers dropped by about 20%, and phosphorus dropped by an incredible 50%.
And the dead zone.
It reacted incredibly fast. Between roughly 1991 and 2001, that massive human-caused dead zone on the Black Sea shelf virtually disappeared. It recovered.
Wow. It's
Yeah.
vanished because the nutrient pollution stopped.
Essentially, yes. It proved on a huge scale that if you cut off the fuel supply, the excess nutrients, these coastal ecosystems have a remarkable ability to heal themselves. Dead zones are not necessarily a one-way street.
That is incredibly hopeful. It shows it can be done. So what are the intentional ways we're learning to turn off this terror? What's the science of recovery?
We're learning a lot, focusing on controlling that nutrient recipe at the source. A big area is smarter farming.
Smarter farming, like using less fertilizers.
That's part of it, using techniques like precision agriculture to apply only what's needed when it's needed, but also using nature-based solutions on the farm, like planting cover crops.
Cover crops, what are those?
These are crops like rye or clover that farmers plant after harvesting their main cash crop, like corn or soybeans. They grow over the fall and winter.
Why do that?
Two big reasons. They help hold the soil in place, preventing erosion. And crucially, they soak up any leftover nutrients in the soil, preventing them from washing away when the winter rains come.
Ah, like nutrient sponges. Clever. What else?
Planting buffer zones. These are strips of grass, trees, or shrubs planted along the edges of fields, especially next to streams or rivers.
Like a green border. How do they help?
They act like natural filters. When rainwater runs off the field carrying soil and nutrients, it has to flow through the buffer zone. The plants slow the water down, trap the sediment, and absorb a lot of the nutrients before the water reaches the stream.
So cover crops and buffer zones help keep nutrients on the farm and out of the water. Smart. What about restoring natural systems?
Absolutely key. Restoring natural filters like wetlands, coastal marshes, and mangrove forests in tropical areas is incredibly important.
Wetlands as filters, I've heard that. How do they work?
They act like giant sponges on the landscape. They soak up rainwater, slow down its flow, allow pollutants to settle out, and the plants and microbes within the wetland naturally process and remove nutrients like nitrogen. They're nature's water treatment plants.
So bringing back wetlands helps clean the water flowing towards the coast. Makes sense. And you mentioned oysters earlier.
Yes. Never underestimate oyster power. Oysters are amazing filter feeders.
How much can they filter?
A single adult oyster can filter dozens of gallons of water every single day. As they filter, they remove algae and sediment from the water, making it clearer.
Wow, dozens of gallons per oyster. Do they remove the nutrients too?
They do, indirectly. They eat the algae that grew because of the nutrients, incorporating the nitrogen and phosphorus into their own shells and tissues. So harvesting the oysters actually removes those nutrients from the water.
So restoring oyster reefs is like building natural water filters.
Exactly. Efforts like the big push to add billions of new oysters back into the Chesapeake Bay are not just about bringing back the oysters themselves, they're about restoring that vital water cleaning function to the entire ecosystem.
That's fantastic. Smarter farming, natural filters, oyster power. It sounds like there are real solutions. Which brings us to us, the listeners. What can regular kids and families do? This seems like such a huge problem.
It is huge, but the amazing thing is everyone can contribute to the solution. Remember how the nutrients come from farms, cities, and the air? We can all take actions that reduce those sources. This is your mission, should you choose to accept it. Become an ocean guardian.
I accept. What's mission number 1?
In your own yard. Think about your lawn or garden. Does it really need fertilizer? Maybe plant native flowers or grasses that don't need extra feeding. If you do use fertilizer, use the absolute minimum amount needed.
Okay, less fertilizer means less runoff. Got it. Mission 2.
Pet waste patrol. Always, always scoop the poop when you walk your dog. Remember, pet waste is packed with nitrogen. Leaving it on the ground means the next rain washes those nutrients straight into the storm drain.
Scoop the poop. Easy enough. What else?
Storm drain awareness. This is huge in towns and cities. Remember that most storm drains on the street lead directly to the nearest river or stream and eventually the ocean. No treatment.
So only rain down the drain.
Exactly. Don't let trash, oil, soap from washing cars, or anything else go down there. Keep the drains clean.
Makes sense. Any other missions for ocean guardians?
One more big one, save energy. Remember how air pollution from burning fossil fuels contributes nitrogen?
Right, the atmospheric deposition.
So anything you do to save electricity at home, turning off lights, using efficient appliances, or choosing to walk, bike, or use public transport instead of driving helps reduce that air pollution. Cleaner air means cleaner water.
Wow, so saving energy helps stop dead zones. It really is all connected.
It absolutely is. Every small action adds up when millions of people do it.
Okay, let's quickly recap our spooky investigation. We learned that ocean dead zones, or hypoxia, are these silent, scary underwater deserts.
Right, caused by that 5-step recipe called eutrophication. An overdose of nutrients fuels a crazy algae party.
The green monster party, which then leads to the oxygen heist by bacteria when the algae die.
And the whole problem gets trapped near the bottom by the layer cake, or stratification.
We found the clues lead back to farms, cities, and even the air, funneling nutrients down rivers like the Mississippi.
And we saw the devastating impact on ocean creatures, the fugitives forced to flee, and the traps left behind in underwater graveyards, plus the invisible wounds and economic costs.
We looked at global hotspots, from the New Jersey-sized zone in the Gulf to the complicated food web collapse in the Baltic.
But crucially, we found real beacons of hope, the amazing comeback of the Black Sea and the steady progress in cleaning up the Chesapeake Bay.
They prove that this terror is reversible. We have the tools: smarter farming, restoring wetlands, unleashing oyster power.
And the power of individual actions by ocean guardians everywhere.
It's been quite an exploration today. A bit spooky, but also full of incredible science and hope.
It really has. And a huge thank you to all our listeners for joining us on this journey into the ocean's hidden challenges.
Before we go, here's a final thought to ponder. The ocean, especially those tiny phytoplankton, works constantly to make oxygen for us. About half the air we breathe comes from the sea.
That's amazing to think about. Half our breath.
So the next time you see rain washing water off a lawn, or down a street, or across a farm field, remember that water is on a long journey.
And we, all of us, have the power to decide whether that water carries life-sustaining cleanliness or suffocating pollution down to the very source of the ocean's breath.
A powerful thought indeed. Thank you again for tuning in.
We really appreciate you being here.
Hope you enjoyed our Halloween-themed topic. Hope to see you next time on Saltwater Stories.